Welcome back, everyone, for another deep dive. This time, we're going to be tackling something pretty powerful. It's kind of the unseen force that drives our modern world, electricity.
Mm.
We'll be using an 11th grade science textbook to guide us, but our goal is to really help everyone listening not just understand the basic concepts, but to really grasp how circuits work and how it all ties into our daily lives.
I think it's a topic that a lot of people find pretty mysterious,
Yeah.
and the more we understand those invisible forces, the more magical it all becomes.
Absolutely. So let's get right into it. What exactly is electricity?
Well, at its core, electricity is about the flow of electric charge.
Okay.
You can kind of picture it like a river,
Hmm.
but instead of water molecules, we've got these tiny particles called electrons,
Right.
and they carry a negative charge, and it's their movement that creates what we call electric current.
Okay, so it's like a river of electrons, basically.
Yeah.
Yeah. But the book mentions something kind of weird about how we actually depict the flow of current. Like it's actually shown as going in the opposite direction of the
Oh,
electrons.
yeah, right. That's kind of a historical quirk. You see, early scientists, um, they didn't know about electrons, right?
Right.
So they thought of it as a flow of positive charge, and that just kind of stuck, even after we figured out that it was actually these negatively charged electrons doing all the moving.
Ah, so sometimes even science gets things backwards. I guess it just goes to show that knowledge is always evolving. But speaking of things that are kind of hard to visualize, the book talks about these units of measurement, like coulombs and amperes. What
Yeah.
are those actually measuring?
Well, imagine you have a bag of electrons. Okay.
Yeah.
A coulomb is basically a giant bag. I mean, it holds like
Yeah.
a crazy number of electrons. Think 6 billion,
Wow.
like a 6 with 18 zeros after it.
That's a lot of electrons.
Yeah. And an ampere measures how fast those electrons are flowing. So 1 ampere means that a whole coulomb's worth of electrons passes by a point every single second.
Wow, that's a lot of electron traffic.
Hmm.
But what's actually making those electrons move? It's not like they just decide to go for a jog, right?
Exactly. Yeah.
Yeah.
That's where voltage comes in. Think of it like the pressure in a water pipe.
Okay.
The higher the pressure difference between 2 points, the more forcefully the water flows.
Right.
In the same way, voltage or potential difference creates kind of an electrical pressure, and that pushes the electrons along.
So a higher voltage means like more oomph behind the electron flow.
You got it.
The book connects this to batteries, those little powerhouses. What's actually going on inside those?
Well, inside a battery, there are these chemical reactions constantly creating a voltage difference
Yeah.
between the positive and negative terminals.
Okay.
It's like a tiny pump that keeps that electrical pressure up and ready to push electrons through a circuit whenever you connect it.
So a battery is basically an electron pump.
That's a great way to think about it, yeah.
Okay. The book also describes volts as a measure of work done to move a charge. I mean, what does that actually mean in practical terms?
It means that voltage tells us how much energy is transferred for every unit of charge.
Yeah.
So a higher voltage can do more work, like, make a light bulb shine brighter
Right.
or make a motor spin faster.
So it's kind of like the muscle behind the electricity.
You could say that, yeah.
Now the chapter also dives into resistance. Is that like the friction in the system?
That's a good way to put it. Uh, imagine pushing water through a narrow pipe.
Okay.
The water encounters resistance, which makes it harder to flow.
Right.
And similarly, in an electrical conductor, resistance opposes the flow of current.
And the book links this to that experiment with the nichrome wire. What was the takeaway from that?
Well, that experiment was great because it showed us how a material's properties really influence resistance. Longer wires, like a longer, narrower pipe, they offer more resistance, and thicker wires, they have less. It all comes down to how easily those electrons can squeeze through.
Ah, so it's like an electron obstacle course. And then the book brings up Ohm's law, which ties together voltage, current, and resistance, VRIR. What's so important about that equation?
Well, it's a simple equation, but it's incredibly powerful. It basically means that you can adjust the current in a circuit by changing either the voltage or the resistance.
So we can kind of manipulate the electron flow by changing the pressure or the obstacles in their path.
Exactly.
That's pretty cool. The book then goes on to talk about resistivity. Is that the same as resistance?
Not quite. Resistance is it's specific to an object, like a particular wire. Resistivity is more about the material itself.
Okay.
So, for example, copper has much lower resistivity than rubber. That's why copper is a great conductor. Well, rubber is used to insulate and stop electricity from flowing where we don't want it to.
So resistivity is like the material's inherent stickiness to those flowing electrons.
You could put it that way, yeah.
And the book mentioned that it can change with temperature, right?
That's right. For most materials, resistivity actually goes up as the temperature rises.
Okay.
Think of it like this. When things heat up, the atoms in the material start vibrating more, and that makes it harder for the electrons to move through smoothly.
So it's like the electrons are trying to navigate a crowded dance floor as the temperature goes up. The textbook has this table that lists the resistivity of various materials.
Right.
What stands out to you when you look at that table?
Well, metals like silver and copper have really low resistivity,
Yeah,
which is why we use them for electrical wiring.
makes sense.
And then on the other end, you've got insulators like glass and rubber, which have very high resistivity, so they're great for keeping electricity contained and preventing those nasty shocks.
Right, right. Now there's this interesting tidbit about alloys often having higher resistivity than the pure metals that they're made of. Why is that important?
Well, that's kind of the secret behind a lot of heating devices. You see, alloys like nichrome, for example, are used in toasters and electric heaters because their higher resistivity means they generate more heat when electricity flows through them.
So we're harnessing that resistance to generate heat.
Precisely. It's like turning that electron friction into useful warmth.
Okay, I like that. So let's move on to circuits. The chapter focuses on two main types, series and parallel. What's the main difference?
Well, in a series circuit, all the components are connected in a single loop,
Mm-hmm.
one after the other. It's like a one-way street for the electrons. The same current flows through each component, but the voltage gets divided among them. And this means that if one component fails, the whole circuit breaks. Like old school Christmas lights,
Yeah.
one bulb burns out and the whole string goes dark.
Oh, I remember those frustrating lights. So series circuits are like a delicate chain. What about parallel circuits?
Well, in a parallel circuit, each component is connected across the same 2 points.
Okay.
So it's like they each have their own separate path for the current. Each one gets the full voltage, and if one fails, the others aren't affected. Thankfully, most of our homes are wired in parallel.
Oh, that's a relief. Parallel circuits are much more resilient and flexible. The book mentions calculating equivalent resistance for series and parallel combinations. Do we need to get into those calculations right now?
I think for now, let's just stick with the big picture. The main takeaway is that adding resistors in series increases the total resistance,
Okay.
like adding more obstacles in the electron's path.
Yeah.
But in parallel, it's actually the opposite. Adding more resistors actually decreases the total resistance because you're giving those electrons more paths to choose from.
Okay, so more paths in parallel means less resistance overall.
Ex-
Got it. Now the textbook points out that current flow always produces heat. Why is that?
Well, as those electrons are flowing through material, they bump into the atoms in the material,
Okay.
and that causes them to vibrate more. And that increased vibration is what we experience as heat.
Right. And when we see that all the time with our devices, getting warm after we've been using them, it's like this little reminder that electricity is energy in motion. But how does that relate to Joule's law, which the book introduces?
Well, Joule's law gives us a way to calculate how much heat is produced. It basically says that the heat generated is proportional to the square of the current and the resistance. So more current or higher resistance means more heat.
So that explains why wires can get dangerously hot if too much current surges through them. It's like trying to force a huge crowd through a tiny doorway. Things are bound to get heated.
Yeah.
But luckily we have fuses to prevent those electrical meltdowns.
That's right. Fuses are like safety valves. They use Joule's law to their advantage. So when the current gets too high, the fuse wire melts, which breaks the circuit and prevents any damage. It's a clever way to protect our devices and wiring from overheating.
So fuses are like the sacrificial heroes of the electrical world, bravely melting away to protect the rest of the circuit. Now, before we wrap up this first part of our electrical journey, I want to touch on how we intentionally put this heating effect expect to work in various devices.
Well, you've got things like electric heaters, irons, toasters, all designed to generate heat for specific purposes.
Right.
Even those old-fashioned incandescent light bulbs, they essentially relied on heating a filament until it glowed. It's all about controlling the flow of electrons and harnessing the heat they generate.
We've come a long way from those incandescent bulbs. And speaking of light, here's a question to ponder as we move on to the next part.
Mm.
If electricity is about these moving electrons, why don't we actually see those electrons flowing? That's a good one.
It's all happening on such a tiny scale, right?
Yeah. We'll explore that more when we come back. Welcome back. It really is a good question, that one you posed about seeing those electrons. They're incredibly tiny and moving so fast. It's more like we're seeing the effects of their movement, not the electrons themselves.
Yeah, it's like we're seeing the footprints of the electricity, but not the actual feet. So the light, the heat, the whir of a motor, these are all signs that those invisible electrons are hard at work.
Precisely. And speaking of work, the textbook introduces this key concept of electric power, which is all about the rate at which electrical energy is used.
Okay.
So think of it like this, right? Energy is like the ability to do work,
Mm-hmm.
but power measures how quickly that work gets done.
Okay, so power is like the speed of energy consumption.
Yeah, that's a good way to put it.
And the equation for power is P via VI, right? Voltage times current. That's right. Power, P equals voltage V multiplied by current, I. And using Ohm's law, we can rewrite that equation in a couple other ways.
Okay.
As P equals I squared R, or P equals V squared divided by R.
So no matter which two variables we know, voltage, current, or resistance, we can figure out the power.
Yeah, exactly.
That's pretty handy. And the unit for power is the watt, which we see all the time on light bulbs and appliances.
Right. So a watt is basically the power that's consumed when 1 ampere of current flows at a potential difference of 1 volt. But when we talk about bigger amounts of energy that are used over time, like in our homes, we use kilowatt hours.
Ah, yes, kilowatt hours, the units that we see on our electricity bills.
Exactly.
It's a reminder that we're literally paying for the work that those tiny electrons are doing for us.
Right. So you've got a pretty good grasp of those fundamental concepts. Current, voltage, resistance, and power. Now let's try to connect those ideas to some real-world scenarios, and let's start with those series and parallel circuits that we talked about earlier.
Okay, yeah, let's revisit those circuits. The textbook really emphasizes that in a series circuit, the same current flows through all the components. Why is that a problem?
Well, as you mentioned before, a single faulty component can bring the whole system down. Like imagine wiring your entire house in series. One burnt out light bulb and your whole house would be plunged into darkness.
Yikes. Not the most practical setup.
Not really, no.
And that's where the parallel circuits come in. They're much more flexible and resilient. The textbook also talks about why connecting devices with really different power needs in series just wouldn't work very well. Can you give us an example of that?
Sure. Imagine connecting like a low-power LED and a powerful electric heater in series. The low resistance of the heater would basically dominate, and the LED would barely get enough voltage to even light up.
So the current would be limited by the device with the highest resistance. In this case, the LED. It's like the heater is hogging all the electrical oomph.
Yeah, that's a good way to put it. But in a parallel circuit, each device gets the full voltage, so they can operate at their intended power. It's just a much more efficient and practical way to wire things.
It's like giving each device its own dedicated power supply.
Right.
Now the chapter talks about how we use that heat generated by electricity in all sorts of everyday devices.
Yeah. You've got electric heaters, irons, toasters. All those things rely on Joule's law to convert electrical energy into heat. And those old incandescent light bulbs, remember those? They're basically just tiny heaters that happen to emit light as a byproduct.
Right. And let's not forget those heroic fuses sacrificing themselves to protect our circuits from overloads.
Speaking of clever design, the textbook mentions that the material that's used for the heating element is carefully chosen based on its resistivity.
Yeah, absolutely. It's not just about generating heat. It's about generating the right amount of heat for the specific application. So for example, nichrome, it has a high resistivity and can withstand those high temperatures. That's why it's often used for heating elements.
So it's about finding the right material with the right resistivity to create the perfect amount of heat. It's
Yeah.
kind of like choosing the right kind of wood for a fire, right?
Right.
Some woods burn hotter and faster than others.
Yeah, that's a great analogy. Now the textbook also touches on the concept of power rating, which is, you often see that on appliances.
Right.
This tells us how much power the appliance uses when it's operating at its normal voltage. Right, right. So a 100-watt light bulb, it uses 100 watts of power when it's plugged into a standard outlet. But
Yeah.
but how does that relate to the energy that we actually consume and get billed for?
Well, energy consumption is basically calculated by multiplying power by time.
Okay.
So if that 100-watt bulb runs for an hour, it consumes 100 watt-hours of energy.
Mm-hmm.
And our electricity bills are typically measured in kilowatt-hours, which is just, 1,000 watt-hours.
Okay, so the longer an appliance runs, the more energy it consumes and the higher our electric bill goes. That's why energy efficiency is so important, especially with things like refrigerators that are running all the time.
Absolutely.
Yeah.
And the textbook even has this practical example where
Yeah.
it calculates the cost of running a refrigerator for a month.
Right.
And it takes into account the refrigerator's power rating, how many hours per day it runs, and the cost of electricity per kilowatt hour.
That's really helpful to see how those concepts translate into actual real world costs. It reminds us that being mindful of our energy consumption can actually save us money in the long run.
Absolutely. Now, before we move on to the final part of our deep dive, here's another question to think about. This one's from the textbook. Why is it that the cord of an electric heater doesn't glow red hot like the heating element, even though
Yeah.
they're both carrying the same current? It seems kind of counterintuitive, right? We'll tackle that mystery when we come back.
All right, we're back. And before the break, we left everyone with a bit of a head scratcher. Why does the heating element in an electric heater, glow red hot while the cord that's bringing it the power stays relatively cool? I mean, it seems kind of strange because they're both carrying the same current, right?
Yeah. Yeah, it is a bit puzzling at first,
Yeah.
but the answer really lies in how resistance and heat they work together. As Joule's law describes it, remember that the amount of heat produced, it depends on both the square of the current and the resistance.
Right, right. Okay, so if the current is the same in both the cord and the heating element, then the difference in the heat must be because of the difference in their resistance.
Exactly. The heating element, it's actually designed to have a much higher resistance than the cord.
Okay.
And this is done by using a material that has a higher resistivity,
Yeah.
and often by making the element thinner and longer. It's almost like we're creating a bottleneck for that electron flow.
Ah, so it's like intentionally making it harder for the electrons to get through the heating element
Yeah.
so that more of their energy gets turned into heat.
Exactly. The cord, on the other hand, well, it's made of good conductor like copper, which has a very low resistivity. And it's made thick enough so that the resistance is minimized, and that ensures that most of that electrical energy actually gets delivered to the heating element where we want it.
It's really cool how we can manipulate the resistance of different parts of a circuit to get such specific results. And the textbook mentions that this same principle is at work in those old incandescent light bulbs too, right?
Yeah, absolutely. In an incandescent bulb, the filament, it's made of tungsten. That's a metal that has very high resistivity and a very high melting point. So
Mhm.
so when current flows through that thin filament, well, that high resistance causes it to heat up so much that it actually glows brightly.
It's amazing how much we can achieve by just understanding and manipulating these basic properties of electricity. The chapter also gets into combining resistors in series and parallel. What's the practical significance of doing that?
Well, combining resistors gives us a way to kind of fine-tune the total resistance in a circuit,
Okay.
which then affects how the current and voltage are distributed.
Mhm.
And this is really important for designing circuits that behave in very specific ways to power all the different devices that we use.
So it's like having a toolbox full of different resistors that we can mix and match to get the exact electrical behavior that we need.
Yeah, that's a great way to think about it. So for example, if we need to reduce the current that's flowing to a delicate component, we might add a resistor in series, kind of like a buffer.
Right.
Or if we want to like divide the current between several components, we might connect them in parallel.
Yeah.
It's all about creating the right pathways and obstacles for those electrons.
It's like an electrical puzzle, figuring out how to arrange those resistors to get the result that you want.
The textbook also provides some formulas for calculating the equivalent resistance for these combinations.
Hmm.
Should we go over those formulas now? I think for our purposes, it's probably more helpful to just stick with the main concepts. So in a series circuit, remember, the total resistance is simply the sum of the individual resistances. Very straightforward.
Okay, so add resistors in series is like it's like adding more roadblocks for those electrons, which makes the total resistance higher. That makes sense. What about in parallel?
Well, in a parallel circuit, it's a bit more complex, but the overall effect is to actually reduce the total resistance. Each parallel branch basically gives the current another path to take, and that makes it easier for the current to flow overall.
So adding resistors in parallel is like building more lanes on that electrical highway. More lanes, less traffic congestion.
Exactly. And these principles are used everywhere in electronics, from the simplest circuits to the most advanced computers and smartphones.
It's really incredible to think about how these fundamental concepts, these invisible forces are behind so much of our modern technology.
Well, as we wrap up our electrifying deep dive into the world of electricity, I wanted to thank everyone for joining us, and a huge thanks to you, expert speaker, for sharing your insights and making even the most complex concepts so easy to understand.
It was my pleasure. I hope everyone found it enlightening. It's a good reminder that even though we can't see those tiny electrons zipping around, they're constantly at work behind the scenes, powering our lives in countless ways.
Absolutely. So next time you flip a switch or plug in a device, take a moment to appreciate those invisible wonders that are
Hmm.
making it all happen. And until next time, keep those minds curious and those knowledge circuits charged up.